Section 17.4, heat transfer and changes in the entropy of the surroundings. Seriously. Okay, so we were talking about ice melting at temperatures above 0 degrees Celsius. We're going to flip it around and talk about water freezing at temperatures below 0 degrees Celsius. Does water spontaneously freeze if the temperature is below 0? Yes, it's not a trick question. And you're like, it's too easy. I asked the second question first because my brain is just not quite right today. So yes, it's spontaneous. Does the entropy of the water change when it freezes? It does change. Does the entropy go down or up? Down. It goes down. So the entropy change when water freezes is less than 0. Does that match up with it being a spontaneous process? No. So how can we resolve that? Well, let's first make sure we're all on the same page as why does the entropy go down when water freezes? It gets more ordered, more organized. The energy is in fewer places. So now the particles can vibrate, but they can't move past each other, and they're not able to rotate. And so there's fewer places to put the energy, and so the entropy is less. It's more organized. So, second law of thermodynamics, for any spontaneous process, the entropy of what increases? The universe. Okay, so that's important because this is a spontaneous process, but the entropy decreased. That appears to violate the second law of thermodynamics, but it actually doesn't, because when we look at this, we're only looking at the entropy of the water. We're not looking at the entire universe. It's hard to look at the entire universe. How do you back up and see it, right? You can't. So we have to distinguish between the system that we're looking at and the surroundings. So if we're talking about water freezing, let's think of water as the system. And you can define the system and the surroundings in many different ways, but we'll call water the system. So if the water that we're watching freeze below 0 degrees Celsius is the system, what are the surroundings? So we have to divide the universe into two pieces, the system and the surroundings. So the water is the system. Everything else. The rest of the universe is the surroundings. Okay, this is a very big piece here. Everything else. So the surroundings is, I'll put a marker on here first. Rest of the universe. So that's a lot. So, second law of thermodynamics says the entropy of the universe increases in a spontaneous process. The entropy of the universe, the change in entropy, is equal to the change in entropy for the system, for the water, and plus the change in entropy for the surroundings, right? If we divide the universe into two pieces, the sample of water and everything else, if we add the change in entropy for both of those things, we should... He's got a t-shirt on that says, "What happens in a black hole stays in a black hole." That's just awesome. I have child-induced attention deficit disorder. Not to make fun of people with attention deficit disorder, because my father and my brother have that, and it is a serious and very real thing. But I have been interrupted by children every 5 minutes for the past 22 years, and so I really just cannot hold a train of thought anymore. The total entropy change of the universe will equal the water, the change in entropy for the water, plus the change in entropy for the surroundings. So the entropy of the system can decrease as long as the entropy of the surroundings increases by a greater amount. This number can be negative, and this number can still be positive, as long as the other number is a larger positive number. So we get a picture here. So here is the decrease in entropy for the water freezing. But the increase in entropy for the surroundings is larger. And so when you add these two together, the entropy of the universe is increasing. It's not very much, but it is positive. So why does freezing the water cause the entropy of the surroundings to go up?
Where did you get a cold stone from?
Well, freezing is exothermic, right? You have to, energy comes out. Energy was in the water. The energy comes out of the water, and where does it go? To the surroundings. It spreads out, right? Entropy is dispersal of energy. This exothermic process, giving off energy, energy is being dispersed. So release of energy into the surroundings increases the entropy of the surroundings. Is that reasonable? Technically. Now, freezing of water is not spontaneous at all temperatures, is it?
No.
It's, 25 degrees or so in here, and there's a water bottle around here somewhere, but it's not frozen, right? Water does not spontaneously freeze above 0 degrees Celsius. Why is it spontaneous below 0 and not above? Well, the magnitude of that change in entropy for the surroundings is dependent on the temperature. So if the temperature of the surroundings is greater, then the increase in entropy is smaller. So let me just read that because I think I did something wrong. The greater the temperature, the smaller the increase in entropy for a given amount of energy being dispersed. So I like the analogy that was actually in your textbook. I don't know if you guys read that, but I read that. That's how I make these slides. So you know that I like to talk about energy as being like money. So say you had $1,000 to give away, energy to disperse, a certain amount of energy. If I give that $1,000 to someone like Donald Trump, is that going to make a big difference in his net worth? No, because he already has so much. $1,000 on top of what he has is nothing, right? What if I give it to Andrew, my 6-year-old? He has like $4.17 or something, right? Giving him $1,000, I don't know if he understands what 1,000 is. They passed day 100 in school, so he knows what 100 is. But I think 1,000 is beyond his grasp. That's a huge change for him, right? So it's the same with entropy. Entropy is a measure of energy dispersal per unit of temperature. Remember the units on entropy? Joules per Kelvin. A given amount of energy being dispersed per unit temperature. So the higher the temperature, the lower the entropy. Dispersing energy into something that already has a lot of kinetic energy, a higher temperature, just really doesn't make much difference. Any questions about that idea? There's some strange ideas in this chapter. So here's our equation. The change in entropy for the universe equals the change in entropy for the system plus the change in entropy for the surroundings. So we're still looking at the water freezing. The change in entropy for the water freezing is negative. So that's that green bar going down. The change in energy for the surroundings is going to be positive at any temperature, but it's going to be larger at low temperatures and smaller at high temperatures. So here in a low temperature situation, the change in entropy of the surroundings is large. And at a high temperature, the change in entropy for the surroundings is smaller. At this temperature, when we add these two together, we get a negative number. This is not spontaneous. Here, we add these two together, we get a positive number, and that process is spontaneous. Any questions? So the change in entropy depends on the temperature.
And the non-spontaneous needs outside help to get to where
Right,
you're spontaneous.
yes. A non-spontaneous process is not impossible, but it's either going to require you to put energy into it, like maybe passing electric current through water. Water decomposing into hydrogen and oxygen is not spontaneous. But if you pass electric current through it, then it becomes spontaneous. So you can put energy into it, or you can couple it with another reaction or equation that is spontaneous, so that that one has a larger change in entropy, positive, than the one that's negative that you're looking at. So when a system exchanges heat with its surroundings, it changes the entropy of the surroundings. So we can use Q sys, that is the heat. Remember Q equals MC delta T? It's that Q. The heat given off by the system, we can use that to quantify the change in entropy of the surroundings at constant pressure. So we can say that the change in entropy for the surroundings is proportional to negative Q sys. An exothermic process giving energy out will have a negative Q. For an exothermic process, energy is being transferred into the surroundings, which increases the entropy. So then we have a positive change in entropy for the surroundings. If we have an endothermic process, Q will be positive. Energy is coming into the system. That means energy is leaving the surroundings. And so the change in entropy for the surroundings will be negative. So if one goes up, one's positive, the other's negative, and they're proportional to each other. We also know that the magnitude of the entropy change is inversely proportional to the temperature. If the temperature is larger, the change in entropy is smaller. If the temperature is small, the change in entropy is larger. And so what we can do is we can take this proportionality and the one from the previous page that says delta S surroundings equals negative Q sys, and we can combine them together, and we end up with the change in entropy for the surroundings is equal to negative Q for the system divided by the temperature. The temperature there is in kelvins, and Q would be in joules. So you get the correct units of joules per Kelvin. If pressure and temperature are constant, so we're not allowing the temperature to change, we're measuring it. We have a T in the equation, but it's not changing. When pressure and temperature are constant, then Q sys is equal to the change in enthalpy for the system. And so then we can get this equation. So that's something we can actually calculate. Change in entropy for the surroundings equals negative change in enthalpy for the system divided by the temperature. So let's do an example. Consider the reaction between nitrogen and oxygen gas to form dinitrogen monoxide. So here's our reaction, and here's delta H reaction. The enthalpy change for the reaction. This amount of energy, 163.2 kilojoules of energy, is released for molar quantities from the balanced chemical equation. So if you had 2 moles of nitrogen, 1 mole of oxygen, that's how much energy would be released. So this is saying calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. So what is the equation we just came up with?
Change surrounding negative delta H system over T.
Yep, not negative delta H system over T. in kelvins. Okay, so this is positive delta H, so making it negative.
Do we have to convert that to joules or keep it in kilojoules?
We should convert it to joules. So negative 163.2. I'm going to kind of do it a TD way. What does kilo stand for? 10 to the third. So this is not proper form, but it gets the job done. So I just put in 10 to the 3 instead of K for kilo. Or you can change it at the end. And 25 degrees Celsius is what in Kelvin? 298. 273 is 0. And so what does this come out to be? I think it was 548. Negative 548 joules per Kelvin. That's the change in entropy for the surroundings.
Well,
That's not so bad, huh? So what's the sign of the entropy change for the system?
Negative,
it's negative.
Why?
because you got a negative number.
Negative is in front of the system.
But this is the entropy change for the surroundings.
Oh, okay.
What's the sign? We can't calculate the number. What's the sign for the system?
It's positive,
Why?
because the delta H is
Put the
positive.
energy is the delta H up there, the reaction.
Has nothing to do with delta H. Delta H is the change in enthalpy. Yeah, not entropy. Most exothermic reactions have a positive delta S, but not all of them. Just looking at the reaction, how can we figure out if the entropy is positive or negative? Moles of gas. How many moles of gas on the reactant side?
3.
3. And how many on the right side, product side? 2. The number of moles of gas goes down. So that's why. You were saying it was negative, and you're right. It's negative. Sorry. But you were saying it for the wrong reason. Sorry, brain. We're both wrong and we're both right. How's that? Equal opportunity. You can't answer this just based on looking at the sign of delta H. That doesn't work. You answer this by looking at what's going on with the number of moles. Now, some reactions you can't just look at. So the change in S for the system is going to be less than 0. So is this going to be, well, let's do the first part first. Determine the sign of the entropy change for the universe. Well, the change in entropy for the universe equals the change in entropy for the system plus the change in entropy for the surroundings. So this is negative 548. We don't know what this one is, but we know that it's negative. So when you add two negative numbers together, you have to get a negative number. So the change in entropy for the universe is negative. Is it spontaneous?
No.
No. Any questions? Pardon me? It's only spontaneous if the change in entropy for the universe is positive. And what we've talked about today are some controlled situations where we can calculate some things. If you let the temperature and the pressure change, then you've got a big mess of trying to figure something out. So I don't usually do the conceptual connection ones, but I thought this one was interesting. Do biological systems contradict the second law of thermodynamics? By taking energy from their surroundings and synthesizing large, complex biological molecules, plants and animals tend to concentrate energy, not disperse it. How can this be so?
Release heat, use release most part energy as heat.
Yeah.
Yeah, what happens when, say, a mouse metabolizes the food that it eats? It generates heat, right? And the heat goes into the surroundings.
Yep.
So even though the change in entropy for the system, the mouse is taking not carbon dioxide, that would be the plants, oxygen from the air and water and proteins and glucose and things from its food, and it's making more complicated molecules. That is a negative change in entropy. And it's often concentrating the energy in that as well.
How does that work with the plant?
Plants take carbon dioxide from the air and water from the soil. They also need trace minerals and stuff, and they make that into
But they're taking
sugars
energy in, right?
and starches and cellulose, but they're also dispersing entropy to the surroundings.
In what form?
They also have light energy coming in from the sun. So if you look at all the components and add them all up, plants and animals do not violate the second law of thermodynamics.
Mainly,
No, individually.
okay, well, I think mainly when plants are eaten, that's when their energy is dispersed.
Yeah.
So they have their energy is potential until ingested.
Until ingested and or they die and they decompose.
And there was another question earlier in this chapter about like eating a vegetarian diet or eating animals, and which one requires more energy, basically. And if you think about the plants take sunlight and carbon dioxide and water and concentrate that, and then you eat it. That's one energy transaction. If you're eating a hamburger, the cow took the plant and ate it,
Yeah.
and then you're eating the cow. So there's more energy transactions, and every time, what do you lose? Energy, the heat tax.
It's even worse, like a second order carnivore.
Second order carnivore.
I only eat things that eat things.
What sorts of second order carnivores do you enjoy?
Lions and stuff.
Lions. That's awesome.
Fish eat other fish.
Fish eat other fish. This is true.
But I'm talking like things that move around.
This is true.
Squirrels.
Squirrels.
Carnivorous. They're carnivorous. Counts.
Carnivorous squirrels. I'm going to turn this off now.